Yeah, that's from psychology. Okay, so I just like a quick question. So I wasn't quite sure what part 2 was, so I did the entire section. Right? Do you want me to go through the entire section or just stick to part 2? Because I put it in because I was thinking of the recap of the first half. That's
perfectly fine.
Where is? Oh, here it is. Yeah, I haven't used this in so long. Okay. So, I'm Matthew Hall. I did my presentation on development of quantum theory. Just a little disclaimer at the start. A lot of these concepts are pretty confusing, but a lot of it is stuff that we've already covered. It's just going a lot more in depth into it. So that's why it may seem like you're getting it, but you're not quite getting it. So just a little tidbit. Okay, so I'm doing like a brief recap of part 1. So Louis de Broglie, I'm just call him Broccoli. Louis de Broglie proposes the question: if electromagnetic radiation can have particle-like character, can electrons and other submicroscopic particles exhibit wave-like characters? So like, the general idea is he's trying to treat each individual electron like it's a wave. So think of several waves like in a wavelength going around the atom instead of each individual atom. Or each individual particle circling the atom. It's a bunch of waves. Okay. He predicted a particle with mass and velocity should display the behavior of a wave. So that's the wavelength is equal to h, which is Planck's constant, which is right there, 6.62607.004 times 10 to the negative 34 meters kilograms per second, divided by mass times volume, which just would equal h divided by p, which is power. So just a bit more recap. Broglie argued that Bohr's assumption of quantization can be explained if the electron is considered not as a particle, but rather as a circular standing wave, such that each an integral number of wavelengths could fit exactly within the orbit. So it's just going over the idea that the electron can be considered as a wave, a circular wave that's traveling around the radius of the atom. Assuming a circular orbit of radius r, and the circumference is 2 pi r, which is the standard radius or circumference of a circle. The de Broglie condition is 2 pi r would equal n times the wavelength. And n would just be equal to 1, 2, 3. N is the number of subshells on the atom. So depending on the number of subshells, it influences the wavelengths of the atom. Yes, thank you. After Broglie's proposal, C.J. Davison and L.H. Germer experimentally show that electrons can exhibit wave-like behavior. So they put a test with a crystalline nickel substance to a diamond. So there's like little slits in the natural atomic structure of the gem so that they could study they could observe the electrons passing through to see if they were waves or not. Then over time they recorded the electrons at seemingly random. So like at the start, a lot of the electrons were going in at random spots, but as they accumulated through the slits, they could see a clear wave pattern going through the slits. It's kind of interesting there. And then measuring the properties. So Werner Eisenberg, after Broglie and Davidson and all those guys released their respective hypothesis, Werner Eisenberg considered that the limits of how accurate we can measure the properties. So there's a very fine line that we can measure between the momentum and the actual particle's position. The Eisenberg uncertainty principle, it's fundamentally impossible to determine simultaneously and exactly both the momentum and position for a particle For a particle of mass m moving with velocity v times x in the x direction, or equivalently with the momentum px, the product of the uncertainty of its position, delta x, and uncertainty of the moment, delta px, must be greater than h2. Sorry. So it's really fundamentally impossible to determine both at the same time with the current limitation, because we can't really get a grasp on it physically with our current technology. And the quantum mechanical model for an atom. So Erwin Schrödinger extended de Broglie's work by incorporating the Broglie relation into a wave equation, deriving what is today known as the Schrödinger equation, which is that. I don't know the characters' individual names, but Schrödinger thought of in terms of three-dimensional stationary waves, or wave functions. That's the symbol here. So that's that symbol in the equation. And later, Max Born proposed an interpretation of wave functions that is currently accepted today, and that is all electrons are still particles. And so the waves represented by wavelength, or wave functions, are not physical waves, but instead are complex probability amplitudes. So just putting that into simple terms, each individual electron is still a particle, but that electron itself has a certain amplitude that makes it display wave-like behaviors. So the work done by Schrödinger, Born, and many others is what's called quantum mechanics right now. All right, part 2. Finally. Understanding quantum theory of electrons and atoms. So this is the portion where we've gone over this before, but it's just now explained more in depth. So you may catch it, you may not. Energy levels in atoms are labeled with the value n, which we covered before. The letters n refers to the principal quantum number, or the location in the energy level. The principal quantum number is also known as the shell number, which is n equals 1, 2, 3, etc. And the further proceed from the nucleus, the higher shell number, and the higher the energy level, to make sure the atom is stable. Okay. The quantum mechanical model for where electrons reside in an atom can be used to look at electrons transitions. The transfer is a high energy level absorbed at, okay. If the transfer is to a higher energy level, energy is absorbed into the atom, but if it's to a lower level, it's emitted. And the energy is lost or gained by absorbing or expelling a photon from the atom, and that's just a light particle, simply. And this process can be summarized in the equation with delta E equals E final minus E initial, or which is equal to this equation right here. And NF and NI are the initial and final positions of the electron orbit. Atomic orbital, it's different from an orbital. It's basically where an electron is at a given point in the orbit. Another quantum number, which is L, angular momentum quantum number, defines the shape of the orbital, which the orbital is not necessarily a perfect ring. It can take a different shape depending on the L. This number takes on the value L equals 0, 1, 2, any value of n minus 1. So, in other words, an orbital with n equals 1 can only have a value of L equals 0. However, n equals 2 allows for L equals 0 and L equals 1. In other words, you can have L equals, etc., depending on what orbital you're in. But the orbitals that are called L equals 1 are the s orbitals that we learned about before. So you can reference this to the electron configuration, and that should help you understand this concept more. While L equals 1 are p orbitals. So S2, P6, D10, etc. There are certain distances from the nucleus at which the probability density of finding an electron located at a particular orbital is 0. In other words, the value of the wavelength function is 0 at the distance for this orbital. Such a value or radius r is called a radial node. Okay, magnetic quantum number. Orbitals with different values of the z component So like on the z-axis of a plane, x, y, z, of the angular momentum will have different energies resulting from interacting with the field. So the magnetic quantum number called ml, or m sub l, you can't put sub on the PowerPoint, specifies that the z component of the angular momentum for a particular orbital. The magnetic quantum number specifies orientation of the orbital in the space, so how it's kind of sitting around the atom, so it can be in several different angles. For instance, L equals 1, ML would equal -1, 0, and 1. Well, L equals 0, ML would equal 0. It's representing the different angles at which the orbital can be in each respective orbit. And the spin quantum number. So it was originally thought there were only 3 quantum numbers, but after further research in around the 1920s, when hydrogen line spectra are examined at extremely high resolution, some lines were actually not single peaks, but rather a pair of closely spaced lines. And these observations led Samuel Goldsmith and George Ulbeck to propose that electrons have a 4th quantum number, and this is the spin quantum number, or ms. Each electron acts as a tiny magnet, or a tiny rotating object with an angular momentum in space. So each electron is, while orbiting, is spinning. Right? This is just the types of spins. A magnitude of overall electron spin can only have one value. An electron can only spin in one of 2 quantized states, and that's spinning in the negative or the positive direction. So one is termed in the state as the alpha state, the z component of the spinning being in the positive direction of the z-axis, which would be ms equals 1/2. And the other is called beta state, with the z component of the spin being negative, so negative 1/2. And this is the Pauli exclusion principle. An electron in an atom is completely described by 4 quantum numbers, N, L, ML, and MS. The first 3 describe the orbital, while the 4th describes the property of the spin. An Austrian physicist, Wolfgang Pauli, formulated a general principle that gives the last piece of information needed to understand the general behavior of electrons in atoms. So the Pauli exclusion principle is no 2 electrons in the same atom can have exactly the same set of all 4 quantum numbers. What this means is that electrons can share the same orbital, the same set of quantum numbers, N, L, ML, but only if their spin quantum numbers, ms, have different values. So, for instance, in the first orbital on hydrogen up there, one has to be spinning positively while the other one has to be spinning negatively. All the other values can be the same, but one of them has to be different. Otherwise, it can't be an individual electron. And this is just a table describing all the different quantum numbers that I was presented in this PowerPoint. Principal number, quantum number, which is n, or the number of orbitals, angular momentum, this is the L value, magnetic quantum number, ML, and the spin quantum number, MS. And if you want to keep that up for a second to take this in, I'm sure, because that's the last slide. Any questions? It's a lot of information.
It's the reason that we're not able to exactly determine what an atom looks like. Is that because we're missing a quantum number of some sort?
To my personal knowledge, I'm not entirely certain on that answer, but I theorize it has to do with human limitation. We can't pick it up because we naturally can't.
Yeah.
Any other questions? No? Okay.
Do you have any questions for them?
I didn't. I decided not to because the concept is really all over the place. So.
I just had to add on one thing. Like when you talked about hydrogen, it has to be 1 electron, so that spin is not possible because if you have just 1 electron, 1/2 spin.
Yes.
Right?
Sorry.
So it starts from helium.
I just tried to think of an example on the spot.
That's fine. I just wanted to.
So that helium. Then
Yes, from helium, so it starts +1/2 and -1/2.
No more? Okay. That's it.
Thank you, Sean, it was a great presentation.